Morning, everyone. How are we doing? Is this working? It was telling me that live streaming wasn't available a moment ago. Questions while we wait for people to come in? Anyone? Carl is asking how we can graphically visualize that the gradient is normal to the level curves. I don't have a good graphical interpretation of that. Yeah. No. Yishen is asking a question about web work. Please click on email instructor in that web work question so I can have access to it. I'll respond via email. There will be 4 web works in total. So 2 more after this one. Abe, I've given page numbers. I don't know what section we were doing. Well, Adam has apparently answered that for us. Thank you. We will do implicit differentiation. Well, I mean, yeah. Will we do implicit differentiation? We'll see. Yishen, you're given f of st and you're asked to find f prime. F prime doesn't make sense here. You've got a function of both s and t, so it's derivative with respect to s or derivative with respect to t. There's no f prime. if you were given df dx, but don't know what f of x actually is, f1 is df dx, yeah, fine. I mean, it's just notation. That's right. I believe the last day of class will be June 2nd. All right, let's get back to work. With an example of what we were looking at last time. Tony is referring to the proof we did yesterday that allows us to see that the gradient is actually normal to the level curves. Let's postpone that discussion until we get to the study of curves themselves, which we will do probably by the end of next week. I mean, the issue is we jumped through that whole section in the book. There's a chapter devoted to curves. We're going to come back and do that. We're going to end with that, in fact. I prefer to end with it than do it in the middle. But it brings up the issue of the proof we just did. So let's not worry about it for now. Let's just take that as a property of the gradient, that the gradient is normal to the level curves and surfaces. And let's consider this example. We have this function g. We're asked to find the gradient of g. And you know what that is. That's dg dx, dg dy. So in this case, 2x minus 4 and 2y. And the gradient at the point 1, 2. When x is 1 and y is 2, there it is. And now we are asked to find the tangent line to the level curve, g of xy equal to 1. So in other words, tangent line at the point 1, 2. But of course, you recognize that this is a level curve. And we saw that the gradient is normal to the level curve, right? So if you were to graph this, whatever that looks like, at the point 1, 2, this is normal to the level curve. Now we want the tangent line. So this is what we want. So the tangent is going to be orthogonal to this vector. Any orthogonal vector will do, except for the 0 vector, of course. So in particular, take the vector 4, 2. This is going to be the tangent vector. And so your tangent line is the point, 1, 2, plus t times the tangent vector. There it is. How are we doing? Well, maybe you're not convinced. Maybe you're not convinced. Martin's asking how we got t, any vector orthogonal to this. Yining, we did not get a normal line here. The gradient is normal to the level curve. So the gradient is this vector here. The gradient is normal to the level curve. So it's orthogonal to the tangent. So here, any vector that is orthogonal to this one will do, in particular 4, 2. Right? The dot product is 0. It's easy to see. But look, let's convince ourselves. Let's convince ourselves that this is correct. And this will solidify our understanding that the gradient is normal to the level curve. Do all tangent lines of any level curves pass through the same point? Yishan, I'm not sure what your question is asking. But let's redo this in a way that we are familiar with. What are we looking for? We're looking for the tangent line. So you know you can use any t as long as it's orthogonal to the gradient. Absolutely. Let's redo this question in a way that you're familiar with. We're looking for the tangent line, so you know all we need is dy dx. You have x squared plus y squared minus 4x is equal to 1. Differentiate the whole equation with respect to x with the understanding that y is a function of x. 2x plus 2y dy dx minus 4 is equal to 0. So dy dx is 4 minus 2x over 2y, and dy dx at the point 1, 2, when x is 1, y is 2, this is 2 over 4, which is 1/2. So your tangent line, y equals 1/2 x plus b. When x is 1, y is 2. So b is 3 over 2, and y equals 1/2 x plus 3 over 2 is the equation of the line. Well, now you're looking at this and you're thinking they don't look the same at all, but if you rewrite this as x minus 1 is equal to 14, or x minus 1 over 2 is equal to 2t, and plug that into there, So y, which is equal to 2 plus 2t. 2t is x minus 1 over 2. So this is 1/2 x plus 3 over 2. Exactly the answer we had here. Yishen is asking, are tangent lines of any level curves passing through the same point? Are they always the same? There are some issues with that. If you have a function, that's never going to happen. If z equals f of xy, if you're cutting, right? I mean, for any point, any fixed point xy, there's only supposed to be one z value. So you're never going to have two level curves going through the same point, period. We could implicitly differentiate with respect to y, and we get dx dy, and you know how those are related, right? Dx dy is 1 over dy dx. So, I mean, you know, there's a bunch of things you can do, but here I just want to point out, we use the property of the gradient that was normal to the level curves to get our tangent line, and it absolutely coincides with our usual way of solving for it. Let's consider another example before we move on. Suppose the temperature at a point XYZ is given by T is given by this, where T is in degrees Celsius and XYZ is in meters. Find the rate of change of the temperature at the point 2 minus 1, 2 in the direction of the point 3 minus 3, 3. And a follow-up question B, in which direction does the temperature increase fastest? And what is the maximum rate of increase? All right. There it is. You know what to do. We want the rate of change of t at this point in the direction of that point. Or really, in the direction of the vector PQ. The vector PQ, which is the vector 1 minus 2, 1. So you understand this to be the directional derivative, right? The rate of change in the direction of PQ. And you know what you're going to do. You're going to transform this into a unit vector by dividing by the length, 4, 5, 6. So that's 1 over root 6. And now all you need is a gradient, and we can take the gradient dotted with you. Gradient of t, 200 minus 2x e to the minus x squared. Times minus 6y and 200 minus 18z so the gradient at the point 2 minus 1, 2. Let's be smart here and say, let me factor out a 200. You have these in every term as well. So that's 4. Minus 4 minus 3 is minus 7. Minus 7 minus 36. That's minus 43. Is that correct? Times minus 4, 6, minus 36. Can anybody confirm that? So the directional derivative dut is gradient of t dotted with u, which in this case 200 over e to the 43 root 6. Dot product of these two things. Minus 4 minus 12 is minus 16. Minus 36 is minus 52. There you go. Yeah. Why? Oh, okay, good. Is this correct? Anybody have that? Have I made a mistake? So that is apparently the rate of change of t in the direction of the point Q. Everybody comfortable with that? For part B, in which direction does the temperature increase fastest? We do not need to include units, let's not worry about it. In which direction does the temperature increase the fastest? You know the answer to that? Fastest increase in the direction of the gradient, which is this direction. And what is the maximum rate of increase? We saw last time, well, I mean, you understand that if you take the dot product of the gradient times a unit vector in its direction, of course, you just get the length of the gradient. So whatever that is. All right. Questions here? Thank you, Brent. It is the norm. Exactly that. Questions? One important application of the derivative, if you think back to Calculus 1, was maximizing and minimizing functions, right? So optimization. If we're asked to find the maximum rate of increase for -2, 1 minus 2, is it just negative of that? No. First of all, it's a completely different point. And consequently, the gradient at that point will be very different in general. There's not necessarily a relationship between a gradient at one point and a gradient at another point, even if that other point is negative of itself. So, yeah. Right. Yeah, so we were talking about optimization, and we had this nice theorem in Cal 1, if you recall. A continuous function on a closed and bounded interval attains an absolute max and an absolute min. Ethan is asking, why did we take the dot product between the vector PQ and the gradient at a point P instead of the dot product between the gradient at point P and the unit vector Q? Q was not a vector here. Q was a point. So we're at this point P, and we want to calculate the rate of change in the direction of the point Q, not in the direction of the vector Q. But you're at a point P, you're standing at a point P, and you're looking towards the point Q. It's very important to understand what the question is asking, and that's what it is here. So don't be fooled on web work or an exam. Q is a point here, not a vector. Right, so we had this nice theorem in Cal 1, and let me ask you, you remember exactly the conclusion here, right? I mean, an obvious question that arises is, where can these max and min occur? And the max and min can occur at critical points or at the end points. We have a similar result in several variables. And to that goal, let me introduce a definition. So Sid is asking, would the max and min be different with respect to different variables? We're actually looking for absolute max and min. Actually, we'll relax that to local, but no. I mean, you're thinking ahead when we introduced the partial derivative, and you're thinking to yourself, could it be maximum in one variable but not in the other? It's a good question, and that will lead us to a very nice observation, which we did not have in a one variable case. But let's hold off on that and introduce the following definition. No, this is not a definition, but rather a theorem. In fact, let me not, I'm jumping the gun here. We have this nice theorem in Cal 1, right? We saw that a continuous function on a closed and bounded interval attains an absolute max and an absolute min. And where did these max and min occur? They occurred at critical points or the endpoints. We have a similar theorem in higher dimensions. Think about generalizing this theorem. A continuous function on a closed and bounded domain attains an absolute max and an absolute min. So it's exactly the generalization you want. It's exactly the same result. Let's draw a picture of what's happening here. In 2D, let's say. Right, so if you have a closed and bounded domain, and you have a function hovering above, if you restrict your attention to the stuff just above it, if this function z is continuous, then there exists an absolute max and an absolute min, right? A highest value of z and a lowest value of z. Question is, where can these occur? In the Cal1 case, they occurred where the derivative was 0, where the derivative did not exist, or, right, so at critical points, or at the endpoints of the interval. What about here? Theorem. If f of xy has a local max or min, at the point AB, and the partial derivatives exist here, then the partial derivatives must be 0. I'm offering this without proof. The proof is fairly simple, and it actually follows from the Cal1 proof. So it really is just an extension. But this motivates the following definition. A point AB is called a critical point if the partial derivatives are equal to 0, or if one of these does not exist. So it's really the same definition as in the one variable case, right? A critical point is a point in the domain where the derivative is 0 or the derivative does not exist. I should point out here that there is not a convention in the mathematical community as far as critical points are concerned. Some people call this a critical point. Either the derivative is 0 or the derivative does not exist. Some books make a distinction. They say a critical point is where the derivative is 0 and a point where the derivative does not exist is called a singular point. So be on the lookout for that. If you're using a different book than ours, the definitions might not totally agree here. And it makes sense to make a distinction sometimes. So sometimes some theorems are more easily stated if a distinction is made versus not. You know, I mean, it's give and take. So look, just be on the lookout. We will be using this as the convention because that's the book we're using. But again, if you're using a different book, they may have a different definition. How could the derivative not exist? You know exactly how. Just take the Cal 1 example. X to the 2/3. This function is continuous everywhere, but the derivative does not exist at 0. So, you know, I rubbed it off a bit fast here. Well, let's... All right. Let's not worry about it. All right, so we have this idea. I mean, the theorem here that I just erased tells us that if where can local max and min occur? They can only occur at critical points. Either the derivative is 0 or the derivative does not exist. Following this in Cal 1, we were able to classify critical points as to whether you were having a local max or local min, and we had two different approaches here. You could do a first derivative chart, or you could do a second derivative test. Here, however, a first derivative chart is going to be a lot more difficult because remember that the partial derivatives of x and y only give you two directions. If you want to check that something is a local max, you need to check in all directions. And that's not going to be very easy to do using a first derivative chart. Luckily for us, we have a second derivative test. Suppose the second partial derivatives of f exist and are continuous on a disk with center A AB where the partial derivatives are equal to 0 at AB. And let me take a moment to point out, if we had used the other form, the other definition, right? Some books say that a critical point is where the derivative is 0. And if the derivative does not exist, they would call that a singular point. Here, all we would have had to say was that our continuous on a disk of center AB, where AB is a critical point. So you know it makes the statement slightly more concise. But here we want the partial derivatives just to be 0. So not the second part. So we could not say critical point here. If we had used the other definition, though, then exactly that. Let D be observe, if you will, that by assuming the second partial derivative exists and are continuous at AB, then this satisfies Clairaut's theorem, and we have equality of the mixed partials. So that's why f of xy is sufficient. In other words, f of yx doesn't come into play because it's the same as f of xy. So let D be this, then 1, if D is bigger than 0 and fxx is bigger than 0, then f has a local min at the point AB. Amar is asking, how can we test whether it's max or min if the second derivative doesn't exist on AB? We'll see an example of that. Yishen is asking, second partial derivatives exist here? Mean all 4 second partial derivatives? Yes, absolutely. Two, if D is positive and fxx is negative, then local max at the point AB. And 3, if D is negative, then F has a saddle point at AB. And I mean, of course, you're questioning what is a saddle point. before that though, Finn is asking, so here AB is what? A critical or singular point? Well, we're not using that distinction, right? The book doesn't make that distinction. So AB is a critical point, but a special kind of critical point where the partial derivatives are equal to 0. So we have to make that distinction. Tony is asking, what is the proof of this? What is the proof of that? You may recognize this as the determinant of a 2x2 matrix made up of partial derivatives. So, I mean, the proof makes use of that. It's a bit involved. Let's not worry about it. Yining is asking, how can we find AB? Well, we'll take some examples, but AB are points where the partial derivatives are 0. Let's consider a few examples. But first, we were going to discuss what a saddle point is. Nobody's brought that up yet. What is a saddle point? And that goes back to what Cecilia was asking. Right? I mean, if you scroll up there, would the max and min be different with respect to different variables? That's what happens at a saddle point. Think of a saddle. You know what a saddle looks like, you know, when you're riding horses. And how would you draw a saddle? You know, maybe it goes down like this, and then right, so you see in one direction, maybe in the y direction, you've got a minimum occurring here, but in the x direction, it's actually a maximum. So that's what a saddle point looks like. Right, very much like a saddle, down like this, but up on the sides, saddle point. Let's take a few examples. All right, there it is. So let's start by finding the partial derivatives with respect to x, partial derivatives with respect to y, and we'll set them equal to 0. Well, in fact, I think it's clear to see here that they're all going to exist. So critical points are going to be where the partial derivatives are equal to 0. Right, so partial derivative with respect to x is this. Partial derivative with respect to y is this. They all exist. They exist at every point x, y. So critical points are where these are going to be equal to 0. So from this second one, x is equal to 2 plus 2y. If you plug that in to here, you get this, and what is that? Y minus 2 minus 4 minus 4y. So 3y is equal to negative 6. Y is equal to negative 2, is that correct? And if y is negative 2, then x is negative 2. So we only have one critical point, the point minus 2, 2. Let's figure out if it's a local max or a local min by looking at the second partial derivative So that is 4 minus 1, which is 3, which is bigger than 0. So now we have to look at this. F of xx is less than 0. So d is bigger than 0. Fxx is less than 0. We have a local max occurring at the point minus 2, 2. We are examining this over an infinite domain, absolutely, right? This is valid for all points x, y in R2, absolutely, an infinite domain. Chris is asking, what is the exact value of this local max? Just plug in that point into the original function. I've rubbed it off now, but whatever it was, plug it in, you'll get a value for z that will be a local max. Consider this, again, just a polynomial in x and y, very well behaved, continuous everywhere, differentiable everywhere, and by that I mean partially differentiable at every point and so on. It's all good. There you have it. And these partial derivatives exist everywhere. So the only critical points are where this is equal to 0. So from the first one, you see that y has to be negative x squared. And if you plug that into the second one, this is 3 negative x squared squared plus 3x is equal to 0. So if you factor out a 3x, you get x cubed plus 1 is equal to 0. So x is either equal to 0 or x is negative 1. So if x is 0, y is 0. And if x is negative 1, y is negative 1. So you have these two critical points. So let's test. Well, let's figure out the second derivatives. 6x f of xy is 3, and f of y is 6y. So at the point 0, 0, d, which is 0 times 0 minus 3 squared, which is minus 9. If d is negative, what do we have? Saddle point at the origin. And add the point minus 1, minus 1. What is happening? fxx at minus 1, minus 1, that is minus 6. Times minus 6 minus 3 squared again. So that's 36 minus 9. 27, is that correct? 27, which is positive. So now we have to look at fxx. At minus 1, which is minus 6. And that is less than 0. So d is positive. Second derivative with respect to x is negative, i.e. local max at minus 1, minus 1. Right. What if the second derivative with respect to x was 0, but d was still positive? Then the test would be inconclusive. Anything could happen, we don't know. So the test would not give us any information here. Do we want to do another example, or are we moving on? Yushen is asking if it's possible that D could be 0. Absolutely. That is possible, and in that case, the test would be inconclusive as well. So anything that is outside of the range of the conclusions would not be giving us any information here. One more example. So all other cases are indeed inconclusive. Absolutely. Let us work out the partial derivative with respect to x. Y is treated as constant here. Derivative of this with respect to x is that. Partial derivative of f with respect to y, e to the x minus 1. Again, everything is defined here. So the critical points are where these are equal to 0. From this second one here, we see that x has to be 0. And if x is 0, from this first one, this implies that y is 0. So there's again only one critical point, the point 0, 0. Take the second derivative with respect to x, y e to the x, mixed partial derivative f of xy, which is e to the x, and f of yy, the derivative of this with respect to y, which is 0. Will we encounter cases where the first or second derivatives are not defined everywhere? In practice, that does happen. The issue with that is then the second derivative test does not apply. So then it becomes difficult to classify the critical points. In general, in some easy cases, it might be easy to figure out, but yeah. So D, which is fxx, fyy, minus fxy, all squared in this case. At the origin, this is 0. That was 0. And this is 1. D is negative. We're done. Saddle point at the origin. Let's go back to the Cal 1 situation where if you had a continuous function on a closed and bounded interval, it attained a max or min, and where did that happen? At critical points or at the endpoints? There are some questions here. Yushen is saying if it's just a third derivatives that are not defined everywhere, then it doesn't matter, right? Because all we've been using are the second derivatives. So if the third derivatives aren't defined everywhere, it's not a concern. Bryn is asking, are these just coincidences or most of the critical saddle points occurring at the origin? Oh, just coincidence. This is just coincidence. Take your partial derivatives, solve for the critical points, whatever happens. So a saddle point means one variable, a max, is occurring, and the other, it's a minimum. Exactly that. It does not say which variable has to be the max versus min. It does not. So Jennifer is asking, if we are dealing with an infinite domain, does that make our local max and min absolute as well? It does not. It does not. Anything can happen. We don't know. We don't have enough information to determine that. So if we, thinking back to the Cal1 result, if we had a continuous function on a closed and bounded domain, we had an absolute max and min. And these could occur only at critical points or the endpoints. The same is true in higher dimensions. If we have a continuous function on a closed and bounded domain, then it has to achieve an absolute max and an absolute min. And these can only occur at critical points inside the domain or analogous to the endpoints of the interval, the boundary of the domain. The boundary of the domain is what you have to cross to get from inside the domain to out. So the max and min can occur at critical points inside or on the boundary. And if you generalize that to 3D, if you have a closed and bounded domain, then and some function in a fourth variable hovering above, as long as it's continuous, it has an absolute max and an absolute min. Where can these occur? At critical points inside or on the boundary, which is your surface here that you have to cross to get from inside to outside of the region. Let's take a few examples to clear that up. We are asked to find the absolute max Amar is saying he has difficulty visualizing the domain boundary of higher dimensional functions. I drew something in in general here, but let's take a specific example. Take a sphere. Well, I mean, not only by sphere, I mean ball, right? So all the points inside, so x squared plus y squared plus z squared less than or equal to 1. So the sphere of radius 1 and all the points inside that sphere. So really the ball of radius 1. The domain, the boundary, if you're inside and you want to go out, the last thing you cross is the sphere of radius 1. The sphere of radius 1 is the boundary of that 3D domain. The boundary in higher dimensions, or in 3D, is essentially the surface you would paint. If you had this region made out of wood, the domain is all the wooden points, and the boundary is what you would paint, what you would apply paint on. You wouldn't apply paint inside, you cannot get inside, but you would apply paint to the outer surface that is your boundary. Now, of course, if you move to even higher dimensions, 4 dimensions, 5 dimensions, then it becomes difficult to draw a picture of what's happening, but the idea is still there. But now here we're in 2D, where it's very easy. And so easy in fact that let's draw a picture of what's happening. We don't need a picture right now, but it's good to have a picture. So the origin, the point 0, 2, when x is 0, y is 2. And the point 4, 0. So we have this triangular region here. This is our domain D. All right. And while I mean, I drew it in the XY plane here, but if you drew this in 3 space, this is your domain. And then you have this function hovering above. Right, so for every point in this domain, you have some z value associated to it, and so on and so on. Question is, what is the largest value of z? What is the smallest value of z? Absolute max and absolute min. Let's work out the partial derivatives. This is 1 minus y. Fy is 1 minus x. Both of these derivatives exist everywhere. So critical points are where this is going to be equal to 0, and you only have the one critical point, the point 1, 1. Now, absolute max and min can occur at critical, well, I mean, the first question that arises, is this point in the domain? It's a valid question. It's not clear, right? Is the 0.11 in here or is it outside? So let's settle that. The line joining these 2 points is what? Well, it's some line, mx plus b. I don't know what it is, but it goes through the point 0, 2. So when x is 0, y is 2. So b is 2, and y is equal to mx plus 2. And it also goes through the point 4, 0 when x is 4, y is 0. So m is easily seen to be negative 1/2, and you get, well, you get, let's write it here, y equals minus 1/2 x plus 2. So is the 0.11 inside or not? When x is 1, this value right here is 3 over 2. So the 0.11 is below that. So it is in the domain. Excellent. So we know absolute max and absolute min can occur at critical points or on the boundary. So now we're going to have to evaluate the boundary. And what is the boundary? It's what you have to cross to get out of the domain. So you can either cross here or there or there. So the boundary is made up of these 3 line segments. These 3 lines together form the boundary of the triangular region. So let's call this C1, C2, C3. And let's look at C1. What is C1? C1 is the line on the y-axis. And when you're on the y-axis, x is 0. X is 0, and y is the variable that is going from 0 to 2. I've rubbed it off, but we had a function. What was our function? X plus y minus xy. So your function, when x is 0 and y is allowed to vary, is just the function y, where y is between 0 and 2. So maximum we have a maximum of 2 at the point 0, 2, and minimum of 0 at the point 0, 0. Right? The point is, in general, you get a function of one variable. And you know how to maximize and minimize that. You can use Cal 1 techniques. You could take the derivative, find your critical points. Maximum and min occur at critical points or the endpoints. Here there are no critical points, so max and min occur at the endpoints. On C2, This is a line segment on the x-axis. So y is 0. And x varies from 0 to 4. And your function, when y is 0, is just a function x. So again, we have a maximum of 4 at the point 0, 4, and a minimum of 0 at the origin. Finally, on C3, y is minus 1/2 x plus 2, where x is between 0 and 4. Right? This line segment here, this hypotenuse, max is at 4, 0, thank you. And your function, when y is on the line, this is x plus y minus xy that is 1/2 x plus 2 plus 1/2 x squared minus 2x so 1/2 x squared minus 3 over 2x plus 2. That's your function where x is between 0 and 4. We're looking for the max and min, and you know what to do. Right, let me call that g of x, if you will. Take the derivative, which is x minus 3 over 2. Critical points, x is 3 over 2. And the function has a maximum and a minimum either at critical points or at the endpoints. So g of 0 is 2. G of 4, if x is 4, that is 2 minus 6 is minus 2 plus 2 is 0. And finally, at 3 over 2, this is 9 over 8 minus 9 over 4. So that is 9 minus 9 over 8 plus 2. 7 over 8, is that right? 7 over 8? So work that out for us. But if that is 7 over 8, then we see that this is the max and this is the min. And if we put everything together, we still have to check. Oh, I need that. We still have to check at the critical point, 1, 1, and you get 1. So now whatever is maximum amongst all those values we found, 1, 2, 0, 4, 0, 2, 0, 7/8. I think it's clear that the maximum is 4. At the point 4, 0, and a minimum of 0 at the origin and also per have I made a mistake here? Was G of 4 really 0? That's 8 minus 6. No, yeah, there you go. That was a 4, and this was a 7/8. There you go. But maximum of 4 at 4, 0, and a minimum of 0 at the origin. There it is. Yes, thank you. G of 4 is 4. Carl, thanks. And the maximum is at 4, 0. Absolutely. Right? This 4 here corresponds to x equals 4, y equals 0 nonetheless, right? Because it's right here. Yishen is saying it's not possible to have 2 points that have the same min-max value. It is. It is absolutely possible. You know that to happen even in the one variable case. So that does happen. It did not happen here, but it does happen in practice. Let's try another one. Yining is asking, why do we need to apply the second derivative test to know if it's a max or min? We don't need to apply that, and we did not apply it here, right? We never looked at the second derivative. Here, we were considering a continuous function on a closed and bounded domain. We knew it absolutely had to achieve an absolute max and an absolute min. And where can these occur? At critical points or on the boundary. And we evaluated that, and that was it. The maximum value was the max. The minimum value was the min. If, however, I mean, it might have been possible, right? I mean, at 1, 1, this is neither an absolute max nor an absolute min. It could be a local max or a local min or a saddle point. We don't know. We never checked. And it doesn't matter. The question wasn't asking us to classify, just to find the absolute max and the absolute min. If the critical point was not in D, we would only test the boundary. Exactly right, Chris. Consider this. Take a moment to graph this domain D here to understand what's happening. X squared plus y squared less than or equal to 3. You know that to be a circle centered at the origin of radius √3. And if you are restricting your attention to x, y being bigger than or equal to 0, this is the domain at hand. There it is. And you understand that, once again, the domain is made up of 3 curves. This part on the y-axis, this part on the x, and that region, that quarter of a circle. All right. Take the derivative with respect to x. Take the derivative with respect to y. And you see that if y is 0, right, I mean, from the first one equal to 0, we get that y has to be 0. And if y is 0, x can be anything. So here you get infinitely many critical points. X can be anything as long as y is 0. So the whole entire x-axis is a critical point. All right. And that actually turns out to be one of our boundary curves anyways. So that's good. Let's call that C1, C2, C3 as we did before. And on C1, x is 0. And if x is 0, your whole function is 0. So that's easy to deal with. On C2, y is 0. And if y is 0, the whole function is 0 again. So that's easy to deal with as well. And on C3, that's part of the circle x squared plus y squared is equal to 3. Or y squared is equal to 3 minus x squared. So if you plug that in, well, let me not use that, but if y squared is this, you get x times 3 minus x squared. Right? On this circle here, on this part of the circle C3, this is what your function looks like, where x is bigger than 0, but less than or equal to root 3. So Quinn is asking if it's possible to have critical points where you have infinitely many critical points, and that's exactly what we have here. That's exactly what is happening. So the answer is yes. You could have infinitely many critical points. There it is. So we're investigating this function. Let's call it g, which is x 3 minus x squared on this domain. And we're asking the question, where is the max and min? What are the max and min? Where do they happen? And you know what to do. Take the derivative. That's the derivative. And critical points here are easily seen to be plus or minus 1. But negative 1 is not in the domain. So this function has max and min that occur either at critical points or at the endpoints. When x is 0, the whole thing is 0. When x is root 3, the whole thing is 0. And g of 1 is 2. So there it is. On your critical points, the function was always 0. On this boundary, which is the same, function was always 0. On this boundary, function was always 0. And on the boundary C3, we had a maximum of 2. And there it is. So, i.e., your function, which is xy squared, has a minimum of 0 occurring on the x and y axes, and a maximum of 2 occurring at when x is 1, y is root 2. There it is. Yeah, exactly that. Exactly that. Because you're outside the domain. So I mean, if you get points outside of the domain, We don't care about those. We are restricting our attention to this closed and bounded domain here. How are we doing here? Questions? Moving on. Maya's asking, why can't the max or min happen inside? It can. It can. Here it just happened not to be the case, but in practice it can happen inside. There's no issue. Inside, but only on critical points, right? It's not going to happen inside on some arbitrary point that is of no importance. So it could happen inside, but on a critical point. We have another way. This 1 here, so somebody's asking how I got the point 1 root 2. This 1 is this one, which is x equal to 1, but that was on the curve. That was on the circle, right? So when x is 1, y had to be plus or minus root 2, but we were restricting our attention to y being positive. So there it is. We have another approach to dealing with boundaries. Let's look, so let's say this, another approach So we have another approach to dealing with boundaries. Let's take an example. Maximize or minimize, well, and minimize some function subject to some condition G is equal to K. Because that's essentially what we've been doing, right? This is your boundary curve, and you were trying to maximize some function on that boundary curve. Take a step back. Take a step back and look at the level curves here. If you draw these level curves, you have this family. So maybe f of xy equals c1, f of xy equals c4, and so on, right? For different c's, you get this family of curves. So maybe f of x, y equals 5, 6, 7, 8, and so on and so on. And if you were to graph that, which is again a curve in 2 dimensions, right? So G is equal to K. Really, we're asking the question, what is the largest level curve that this will intersect? Right? So what is the largest level curve? What is the largest C which this function intersects? Well, according to the picture we have here, it's f of x, y equals 8. But more importantly, observe what is happening here. The tangent lines have the same slope. So the normal lines have the same vector. But the gradient is normal to the level curves. So the two gradients have to be multiples of each other. This is the idea behind Lagrange multipliers. If you are trying to optimize a function subject to some constraint, the gradients have to be multiples of each other. Let me state this as a theorem, right? Because all we've done here is give you a picture of what's happening. Let me state it as a theorem known as Lagrange multipliers. Let some function f have a max or min at a point on some level curve or surface G equals K, where the gradient of G is not 0. Then the gradients of f and g have to be parallel. Carl is asking, so G is the boundary? Correct. Exactly that. G is the boundary. So that's the Lagrange multipliers theorem as stated in the book. Most books have a different version of that, so let me discuss it. In case you're looking at another book. Most Most books will require k to be 0 here, meaning that you're bringing everything to the left-hand side. So in other words, you really have your condition here, g equals k, is really some function h equal to 0, where h is g minus k here. And most books will define a Laplace operator L as f minus your function, f minus lambda g. And in that case, you require the point to be a critical point. So Lx should be 0, Ly should be 0, Lz, if it's a function of 3 variables, should be 0, and L lambda should be 0 again, which is really the condition that g equals k. So again, the point is, some books introduce this. Our book does not, but most books do. So if you pick up a different book and the Lagrange multipliers is done in a slightly different approach, don't be worried. It's equivalent. Here, L for Lagrange. It's just a new function, f minus lambda g. Most books introduce this Lagrange operator, and the whole Lagrange business can be done according to this function L. Let's take a few examples to clear everything up. We are asked to find the max and min subject to the following constraints. Is lambda an arbitrary constant? Yes. Yes. The idea was that the gradients have to be parallel, so they have to be multiples of each other. There has to exist a lambda, a constant, where these are equal. Consider this, right? You have, so I mean, what is happening? I'm not going to graph this because I don't know what the graph looks like, but when y is 0, x is plus or minus root 5. And when y is 0, I mean, when x is 0, y is 4th root of 5. And I mean, you know it's continuous. So it's going to go from here to there. And you know it's odd. I mean, you know it's even in terms of x and in terms of y. So there's symmetry this way, and there's symmetry that way as well. So, you know, I mean, it looks something like this. Oval shape-ish, something like that. So we have this function hovering above just this, right? Not the inside. We're not trying to maximize on the inside. It's just on this boundary curve. There it is. So your f is this. Your g is x squared plus y to the 4. Like I said, a lot of books will bring the 5 to the other side. But you don't have to, so just be careful. And we need, so gradient of f is lambda gradient of g. Gradient of f, what is the gradient of f? 2xy and x squared. Gradient of g, 2x and 4y cubed. So what do we need? We need 2xy to be lambda 2x and x squared to be lambda 4y cubed. Along with this last condition. And now, what do you have? Just take a step back, 3 equations, 3 unknowns, x, y, and lambda. So solve however you can, however you want to, do whatever you want to do. What do we want to do? Well, let's get rid of the lambda here. If I multiply this whole equation by x, and if I multiply this whole equation by 2y cubed, then the right-hand side will be 4 lambda xy cubed, 4 lambda xy cubed. The right-hand sides will be the same. So I can subtract them and get rid of the right-hand sides. So what? 4xy to the 4 is equal to 4 lambda xy cubed. And same thing here, x cubed is 4 lambda xy cubed. So if you subtract them, 4 4xy to the 4 minus x cubed is equal to 0. So here, if we factor out an x, we get 4x to the 4 minus y squared is equal to 0. So either x is equal to 0 or 4y to the 4 is equal to x squared. And if x is equal to 0, combined with this, we see that y has to be plus or minus 5 to the 1/4. So you get 2 points here. And if this is true, if x squared is this, then you get 4y to the 4 plus y to the 4. Is equal to 5. So that 5y to the 4 is equal to 5. So y is plus or minus 1. And if y is plus or minus 1, x squared is plus or minus 2. So if y is 1, x is plus or minus 2. So from here we get 4 points. If y is 1, x is plus or minus 2. And if y is minus 1, x is plus or minus 2 again. So 4 points here, 2 points there. So now let's plug everything into there and see what is largest. Well, at 0, if x is 0, the whole thing is 0. And if x is plus or minus 2, this, since you're squaring, it doesn't matter which one, that's going to be 4. And if y is minus 1, that's going to be negative 4. There you go. So here we see that this is the max, and this is the min. How are we doing here? Let's try a few more. Same question. Maximize the given function subject to Yishen is suggesting that we can use the previous way to solve this. Absolutely. Absolutely. All you need to do is define, well, but you see the whole boundary the whole boundary here was x squared plus y to the 4 is equal to 5. So you could have said x squared is 5 minus y to the 4. Plug that into there. So your function would then become 5y minus y to the 5, where y is between negative 5 to the 1/4 and 5 to the 1/4. And you're maximizing and minimizing this function on that interval. It's a nice exercise to do it and convince yourself that you get the same answer. Now you see, that is the whole boundary. This is the whole boundary. We weren't looking at the stuff inside. There is no inside, right? That's why I graphed it originally. This was the ellipse shape. There's nothing inside. There's no interior. It's just this. Well, now you're asking the question, how do you know? How do you know that they didn't want inside as well? How would the question have been formulated in that way to distinguish between wanting the inside and not wanting the inside? It's a valid question. So how do you formulate to include the inside? Take your equation again. Less than or equal to, exactly that, Isha. If it's less than or equal to, it includes everything inside. So now you would take your critical points, see if they live inside, and then do the boundary. And the point is, you can now do the boundary using Lagrange multipliers. You now have options. You can describe your boundary and look at your function on the boundary, which is what we were doing before. And now you've got a function of one variable only. You can differentiate and find the max and min, or you can apply Lagrange multipliers. Consider this. It's the same thing here, right? You have this function on this boundary. You know what that is. This is y equals 2x. It's just a straight line. Now it's clear that there's nothing inside, right? You're living on this line. So you could solve for y, right? Y equals 2x. You could plug in 2x in for y, and now you would just have a function of one variable, where x can be anything. X varies from negative infinity to positive infinity. So you could translate this into a function of one variable and do the regular Math 140 business, and that would be fine. But let's do it using Lagrange multipliers instead. Your function g is 2x minus y, and we want the gradient of f to be a multiple of the gradient of g. What is the gradient of f? Right? Well, I mean, look, let me say this. What does this mean? This is fx, fy, perhaps an fz. So in other words, this could be rewritten, if you will. Fx is lambda gx, fy is lambda gy. just a different way of rewriting the same thing. So fx, derivative of this with respect to x, is what? It's a product, so product rule applies. Y e to the negative x squared minus y squared, plus leave the xy fixed, differentiate the exponential, times the derivative of the inside, and that should be equal to lambda times the derivative of g with respect to x, so 2 lambda. Same thing when you differentiate with respect to y, x and that should be equal to lambda gy, which is -1. Along with let's say and 2x minus y equal to 0. All right. All right, all right, all right. What do we want to do? Whatever you want to do. Doesn't seem to be anything good to do here. Let's multiply this one by 2. So I'll get it minus 2 lambda here. And here I've got a 2 lambda, so then I'll add them together. And these will disappear. So if you add these together after multiplying by 2, what do we get? We get y plus 2x e to the minus x squared minus y squared. And then this xy e to the minus x squared minus y squared. This plus twice these, so minus 2x minus 4y is equal to 0. Is this any good? I don't know. Let's factor out an exponential. So I get y plus 2x minus 2x squared y minus 4xy squared. And the exponential itself is never 0. So what is that? Well, maybe now we want to couple with the fact that y is 2x. So we could plug that in. So, you know, this is never 0, so we need the stuff in the brackets to be 0. And let me replace y with 2x. So you get 2x plus 2x minus 2x squared. Y is 2x minus 4x. Again, I'm replacing y with 2x. And so you get this. So that is 4x minus 4x cubed minus 16x cubed. So that is 20. Let me factor out a 4x. 1 minus 5x squared. So x is 0, or x is plus or minus 1 over root 5. And if x is 0, since y is 2x, y has to be 0, and if x is 1 over root 5, y has to be 1 over root 5. So we get 1 over root 5, 1 over root 5, or minus 1 over root 5, minus 1 over. This is not 1, but rather 2. There you go. So 3 points. And f at the origin, that turns out to be 0. F at the point 1 over root 5, 2 over root 5. That was xy, so 2 over 5, e to the this squared plus that squared, negative. So e to the negative 1. And f of minus 1 over root 5 minus 2 over root 5 gives us the same thing. So this one is the minimum, and these two are the max. Same value occurring at 2 different places. How are we doing here? Questions? Do we have time for one more? Let's do a quick one. Only to point out that this Lagrange multipliers business actually extends to more constraints. In the following way, optimize f subject to g equals k, h equals c, then the gradient of f must be a multiple of these two gradients, lambda gradient of g plus mu gradient of h. Let's take an example to illustrate. right? So here, let's rewrite this as x squared plus y squared minus z squared equal to 0, right? It's important to get it equal to a constant, so in this case, 0. So here, your g is x squared plus y squared minus z squared, and your h is x plus y plus z. So the gradient of f should be equal to a combination, linear combination of the gradients gradient of f here, 0, 0, 1. Gradient of g, 2x, 2y, minus 2z. Gradient of h, 1, 1, 1. So that is 2 lambda x plus mu, 2 lambda y plus mu, minus 2 lambda z plus mu, and that is equal to 0, 0, 1. So you get 3 equations, right? 2 lambda x plus mu is equal to 0. 2 lambda y plus mu is equal to 0. And minus 2 lambda z plus mu is equal to 1. Along with both of these two original equations as well, right? Don't forget about those two. So 5 equations, 5 unknowns. You can solve for x, y, z, mu, lambda. You don't actually have to solve for mu and lambda. All you're interested in are the points x, y, z. So sometimes it's possible to get around solving for mu and lambda, but whatever you want to do. If we subtract the 2 here, let's say this minus that, the mu's cancel out, and you get 2 lambda x minus 2 lambda y is equal to 0. And if you factor out a 2 lambda, you get this. So either lambda is equal to 0 or x is equal to y. But if lambda is equal to 0, it's easy to see that mu has to be 0 from the first one. And then from the third one, if lambda is 0, then mu has to be 1. So that leads to a contradiction. So that's out. So right away, you have x has to be equal to y. Okay. So x is equal to y. Then what? Well, if x is y, then from here, you get that z, which is 24 minus x minus y, x is equal to y, so that is 24 minus 2x. And from here, if x and y are the same, then you get 2x squared minus z squared is equal to 0. So z is plus or minus root 2x. And if you plug that back into there, you're done. So if z is root 2x, that is equal to 24 minus 2x. So bring this to the other side, and you get 0 is 24. Well, bring this to the other side, and you get 2 plus root 2. X is 24. So x is 24 over 2 plus root 2. And if z rather is minus root 2x, and that's still 24 minus 2x, so it's easy to see here that x is 24 over 2 minus root 2. So that's what x is, and that's what, right, so that's what x is. Y is equal to x. So you get the points 24 over 2 minus root 2. Y is the same as x. So 24 over 2 minus root 2. And x and then z is negative root 2. So minus 24 root 2 over 2 minus root 2. That's 1 point. And if x is the other one, 24 over 2 plus root 2. Y is the same. And z is root 2x. So 24 root 2. And it's obvious. Can I say lambda and mu cannot be 0? You cannot say that in the beginning, no. Because if lambda and mu are 0, well, if they're both 0, it works out fine here. It does not work here. So you're correct that they cannot both be 0. But you know, you want to adjust in every situation. That's all I'm saying. So, I mean, if you're asking in all cases, can you conclude lambda and mu cannot be 0? The answer is no. It's clear, right? Since your function was just z, so it just depends on this last components here, that this will lead to a minimum, and this will lead to a maximum. Right? This is the max, and this is the min. How are we doing here? Questions? Anybody? Looks like a good place to end. Anybody have any questions? No? We're good? I've posted a new web work, right? Web work 3, so have a look at that. Thank you all for coming, and I will see you tomorrow. You guys have a good one.